Lesson 5-7, Viscosity, Poiseuille's law, and turbulence. Viscosity is fluid friction. Viscosity is the property of fluids that keep it from flowing well. We have two types of flow. We have laminar flow. Laminar flow is when it's smooth, flows in layers, it don't mix, so it's just a nice constant flow. Turbulent flow is like at the top of that picture. There's eddies and swirls that mix the layers of fluid. Turbulent flow is slower than laminar flow because the fluid keeps swirling around. Viscosity is measured by putting a little bit of fluid between two plates, and then the top plate is moved. Friction will cause the fluid to move also. And viscosity, this letter eta is viscosity, is our force times the distance between the plates over the speed that the plates are pulled apart and the area. Laminar flow in tubes. The difference in pressure causes the fluids to flow. And so it turns out the flow rate is a difference in pressures over the resistance. Oh, but how do we get the resistance? Well, that's Poiseuille's law. Poiseuille's law gives you the resistance with viscosity, and it is 8 times viscosity times the length of the tube divided by pi r to the 4th, where r is the radius of the tube. So then after you calculate that, you can plug it in here and get the flow rate. Notice it's r to the 4th. That indicates that the resistance is most affected by the radius. Since the flow rate depends on the pressure, a higher pressure difference means a higher flow rate. However, a higher resistance means a higher pressure difference is needed to maintain the constant flow rate. In blood vessels, this is a problem with plaque on the artery walls. So you'll get the narrower area, the narrower vessel, and so there's a higher resistance. Since there's a higher resistance, you'll have to have a higher pressure to get the blood to flow through that. So how to tell if laminar or turbulent flow? Well, a low speed flow with a smooth, streamlined object is laminar. A high speed or rough object is turbulent. So we have Reynolds number. Gives us a number that we can calculate. If the Reynolds number is below 2,000, it's laminar flow. If the Reynolds number is above 3,000, it's turbulent flow. And if it's in between, it depends on the conditions. Reynolds number is 2 times the density times the speed times the radius of the tube divided by the viscosity. So here we have a syringe giving this person a shot, and it's filled with a solution whose viscosity is this. So that's our viscosity. The plunger area, so that's our area, and the length of the needle, so that's our L. The internal radius of the needle is this, that's our R. The gauge pressure in the vein is that, so this is a pressure. What force must be applied to the plunger so that we have that much volume in that much time? Well, this is a little bit complicated. So I'm going to have to look at a few things. So we're going to end up using Q is our difference in pressures over R. But to do that, we need to calculate all these different things. So Q is V over T. So that would be our volume, 1.0 times 10 to the negative 6, over our time of 3 seconds. So our flow rate is 3.333 times 10 to the negative 7 meters cubed per second. We also need to know the R. Okay, so R is 8 times viscosity times the length over pi r to the 4th. So that'll be 8. The viscosity was 1.5 times 10 to the negative 3 Pascal seconds. The length, it said, was 0.025 meters divided by pi, and the radius, it says, is 4.0 times 10 to the negative 4 meters, and that's to the 4th. Put that in a calculator, and our resistance is 3.730 times 10 to the 9th Pascal seconds per meter cubed. All right, to calculate the rest of it, I think I need to go to a new page. So keep track of that. And we'll come back. All right, so we're going to use our flow rate equals our difference in pressures over the resistance. All right, we had our flow rate was 3.3 times 10 to the negative 7 meters cubed per second. Our difference in pressures we don't know, but we do know that the pressure in the arm, that was P1, is 1900 pascals. And we know our resistance is 3.730 times 10 to the 9. All right, so let's multiply by the 3.73. And I think we get 1243 pascals equals P2 minus the 1900 pascals. Add the 1900 pascals, and we get 3143. All right, so that's our pressure in the needle. So the pressure, or in the syringe. So pressure is force over area. So we know our pressure is 3143. We're looking for the force. The area of the syringe is 8.0 times 10 to the negative 5 meters squared. So multiply, and your force is 0.25 newtons. Very easy to push that. The next question is it laminar flow? Well, you'd have to calculate the Reynolds number. And to calculate the Reynolds number, we need to know the speed. We were not given the speed of the flow. So we do know the flow rate, which was 3.3 times 10 to the negative 7. Flow rate could also be the area times the speed. Well, our area in the needle, so we're talking about in the needle here, is be pi times the radius. And the radius in the needle was 4 times 10 to the negative 4. So it's pi r squared times v. So divide, and you find that the speed in the needle is 0.662. So that's in the needle. So then our Reynolds number is 2 times the density times the speed times the radius divided by the viscosity. Let's assume our solution is essentially water. The speed we just found to be 0.662. And the radius in the needle is 4 times 10 to the negative 4 meters. And the viscosity, it said the solution's viscosity is 1.5 times 10 to the negative 3 Pascal seconds. Run that through your calculator and you get your Reynolds number of 535. So, is that laminar? Well, it's laminar if it's less than 2,000. That is definitely less than 2,000. So, yes, it is laminar. Let your answers flow onto your paper. Have a good day.